This video is about some useful probability models. By the end of this video, you should be able to determine if a situation is a Bernoulli trial. You should be able to use the geometric model to calculate the probability of a first success occurring. You should also be able to use the binomial model to calculate the probability that there are x successes in n trials, and also explain when we can use the normal model to approximate the binomial model. First, let's talk about Bernoulli trials. Bernoulli trials have these three properties. First, there are only two possible outcomes, success and failure. Okay, now you can also think about rolling a dice as having two possible outcomes. If you wanted to roll a 3, then a success would be rolling a 3, and a failure would be not rolling a 3. Okay, so there are only two possible outcomes, success and failure for each trial. Number 2, the probability of success is constant with repeated trials. So if I roll a dice over and over and over again, the probability of success will be the same for each trial. Number 3, the trials are independent of each other. Okay, the previous outcome or past outcomes won't affect future outcomes. Okay, now the question is, are the following Bernoulli trials? Number 1, we roll 50 dice and find the distribution of the number of spots on the faces. Okay, this is not a Bernoulli trial because there are not only two possible outcomes. I'm not looking at success or failure. I'm looking at a distribution. Okay, so this is not a Bernoulli trial. Number 2, you roll 5 dice and you need to get at least 2 6s to win the game. Okay, a success would be rolling 2 or more 6s, and a failure would be rolling, only 1 or 0 6s. Okay, if I did this over and over again, the probability of success would be the same and the trials would be independent. So these are Bernoulli trials. Number 3, we deal 5 cards and get all hearts. Okay, now the truth is there would be two possible outcomes. Success, meaning I got all hearts, and a failure, I didn't get all hearts. But because we're dealing with cards and there's a finite number of cards, 52 cards, the probability of success would not be constant. Okay, if I pull up a card and I get a heart, that changes the probability for the rest of the cards because now there's one fewer heart in the deck. Okay, so that would not be a Bernoulli trial unless I was reshuffling between each card draw, and that would not happen with dealing 5 cards. Okay, last. A company realizes that about 10% of its packages are not being sealed properly. In a case of 24, is it likely that more than 3 are unsealed? Okay, in this case, a success would be it is sealed. A failure would be it's not sealed. We think about the probability of success as constant, a constant 10%. I guess it'd be 90% would be the success because it would be sealed. And we think about, we're assuming that the packages are independent of each other, which may not be the case because there may be one of the 10 machines that are not functioning properly. But assuming that they're independent of each other, number 4 would also be a Bernoulli trial. The first model we will discuss is the geometric model. The geometric model describes how long it will take to achieve the first success in a series of Bernoulli trials. Okay, so for example, if the probability that I make a free throw in basketball is 25%, and that's constant, a constant 25%, what is the probability that I make my first free throw of the game on my first attempt? It'd be 25%. Okay, the second attempt, for my first success to be on my second attempt, I'd have to miss it the first time and then make it the second time. Okay, if the probability that my first free throw of the game is on my third attempt, I will have had to miss it twice and then make it. Or the fourth attempt would be I'd have to miss it 3 times and then I'd make it. Or for the xth attempt, I would have to miss it n minus 1 times and then make it. Okay? So that kind of will help us derive a formula for the geometric model. Okay? We also might expect that I make it on my 4th attempt. So here is the geometric model. The P is the probability of success, and Q is the probability of failure, and X is the number of trials until the first success occurs. Okay? The formula is Q to the x minus 1 times P. Or in other words, we've had x minus 1 failures and then our first success. Okay? The expected value, or the center of this distribution, would be 1 over P, and the standard deviation would be the square root of Q over P squared. You can look at the textbook for how that's derived. On your calculator, you can find these under second vars, which is the distribution menu. Under E, Geomet PDF, the geometric probability density function, tells you the probability that the first success occurs on the xth trial. Okay? F, the Geomet CDF, the geometric cumulative density function, tells you the probability that the first success occurs on or before the xth trial. Now, let's talk a little bit about independence. It is okay to assume independence when dealing with free throw shots and dice rolls because there are theoretically infinitely many of them. Okay, but what about finite sets like drawing cards from a 52 card deck, or the students in your high school, or the songs on your smartphone? Okay, these are finite sets, and so it's not truly independent because after you select one, you won't select it again, and so the probability is changing and they're not independent. Okay, the truth is, if the independence assumption is violated, we can still proceed as long as the sample is smaller than 10% of the population. That's our rule of thumb. If we are sampling less than 10% of the population, it is okay if they're not independent of each other. Okay, this is known as the 10% condition. Okay, the binomial model is the second model that we'll talk about. The binomial model describes the probability that you will have X successes in N Bernoulli trials. Okay, so for example, if there's a dice game where you roll 5 dice and you want to roll 5s, okay, you can look at rolling 2 5s or 3 5s or 5 5s. Okay, you're looking at a certain number of successes and a certain number of trials. Okay, now the computation is a little more complicated for a binomial model, but I'll walk through this hopefully slowly. Okay, let's look at this dice game with 5 dice. Okay, and let's focus on first, I want to roll exactly 2 5s. Okay, now in order to roll exactly 2 5s, that means I also have 3 non-5s. Okay, so it looks something like this. Okay, 1/6 is getting a 5, and I have 2 of them. Okay, and 5/6 are non-5s, and I want 3 of them. Okay, but the problem is that I could order these differently. Okay, for example, my first 2 dice might be 5, and the last 3 might be different numbers, or the first and third, or first and fourth, or second and and sixth. The ordering could be different for these 5 dice. Okay, so you have to take that into account. And there are 5 choose 2 ways to order these 2 things. Okay, which is computed as 5 factorial divided by 2 factorial times 5 minus 2 factorial, or 10. There are 10 ways to order 2 things within 5 things. Okay, now, I don't know why, but in college mathematics, they tend to use this symbol more than they use this one. Okay, so that is commonly seen on the AP exam in our textbook. This 5 choose 2 notation is commonly used. So be aware of that notation as well. So the probability of rolling exactly 2 5s is 5 choose 2 times 1/6 squared times 5/6 cubed, which is about 16%. So the probability that you roll exactly 1 5 is 5 choose 1 times 1/6 to the first times 5/6 to the fifth. Okay. Now we'll notice some patterns here in that when you want exactly x 5s, then it's 1/6 to the x because I want that many. I want x 5s times 5/6 to the 5 minus 1. These are my failures or my non-5s. Okay. We also might expect to roll about 5 times 1/6 or 0.83335s, meaning I probably will get 1 or no 5s would not be uncommon. Here is a summary from the textbook about the binomial model. N is the number of trials, P is the probability of success, and Q is the probability of failure. X is the number of successes in N trials. Okay, so it's computed by N choose C, P to the X, Q to the N minus X. And they chose to use the N choose X notation here, but you will see it written this way, N choose X, in other places. Okay, and again, N choose X is the number of orderings of X things in N things. P is you're looking for X successes, and Q failures. Okay, now the mean of this distribution is N times P, and the standard deviation is the square root of NPQ. Okay, I would memorize these for all my AP Stats students. Questions like this will come up as we're reviewing for the AP exam. So memorize the mean and standard deviation for the binomial model. On your calculator, you can find these under second var's distribution menu. Under A, binom PDF, or the binomial probability density function, tells you the probability that there will be exactly X successes out of N trials with a probability of success of P. Okay, and the binom CDF is the binomial cumulative density function, tells you the probability that there will be X or fewer successes out of N trials with a probability of success of P. Finally, I want to draw a connection between the binomial model and the normal model. Here is an overview for statistics. Again, we have a population that we want to know something about. We randomly draw a sample. Okay, we collect data from that sample and analyze that data, hoping that we can draw conclusions about our population from that random sample. Okay, now as we analyze the data, we will frequently ask questions like, how likely is it that I saw this happen in my sample of 50 people or 40 people or 25 people? Okay, now those can be thought of as a binomial model, meaning I'm looking at having X successes out of my sample of N. Okay, and so you can answer these questions with the binomial model or the normal model. Okay, so for example, how likely is it that I saw 12 or fewer successes in my sample of 50? Or how likely is it that I saw more than 451 successes in my sample of 500? Okay, we could use the binomial model because these are binomial type questions. Okay, but for computational ease, we usually use the normal model. But using the normal model to approximate for the binomial model only works when our sample is large. After all, the binomial model is a discrete model and the normal model is a continuous model. Okay, our rule of thumb is that if we expect to see at least 10 successes and 10 failures, then we can use the normal model to approximate the binomial model. Okay, and this is called the success-failure condition, and we'll use this consistently throughout the rest of the course. So this video was about Bernoulli trials, about the geometric model, and about the binomial model. And two really important ideas that came out of this was something called the 10% condition and something called the success-failure condition, which are two conditions that we will commonly use when looking at other models throughout the rest of this year. Thank you so much for watching.